Have you ever wondered how the exact amount of a substance in a solution can be determined using electricity? Welcome to the fascinating world of coulometry. This intriguing field of study is all about the transformation of matter through electrolysis reactions, and how we can actually measure this process using electricity, specifically in units known as coulombs. It's as if we're unlocking the secret language of molecules, translating their chemical conversations into a language we understand, the language of electrons and energy. And the beauty of it all? This method is incredibly precise, allowing us to determine the exact amount of substance transformed down to the tiniest particle. It's like having a superpower, only this one is real and grounded in the principles of chemistry. Imagine that. Now, isn't that electrifying? So buckle up, because we're about to delve deeper into the theory and principles of coulometry. At the heart of coulometry lies Faraday's laws of electrolysis, which provide a solid theoretical foundation. Let's dive into the world of electrolysis, where Michael Faraday's two laws steer the ship. The first law states that the amount of substance produced at an electrode during electrolysis is directly proportional to the quantity of electricity that passes through the solution. So, if you double the amount of electricity, you'll double the substance produced. Simple, right? The second law of electrolysis delves a bit deeper. It tells us that for a given amount of electric charge, different substances are deposited or dissolved in a ratio of their chemical equivalent weights. This means that if you have two substances and one has twice the equivalent weight of the other, the one with the larger equivalent weight will be deposited or dissolved at half the rate of the other. Now, where does coulometry fit into all of this? Coulometry is a method of quantitative analysis that uses these laws to measure the amount of substance transformed during an electrolytic process. The term coulometry itself comes from coulomb, the unit of electric charge. The beauty of coulometry is that it uses electrical measurements to quantify chemical reactions, bringing together the worlds of physics and chemistry in harmony. In coulometry, the total amount of charge or current passed is measured, and this information is used to determine the amount of a substance involved in the chemical reaction. This is possible because, as Faraday's laws state, the amount of substance consumed or produced at an electrode during electrolysis is directly proportional to the amount of electricity passed through the solution. So, when a known quantity of electricity is passed through a solution containing an unknown quantity of a certain substance, the quantity of that substance can be determined. This is done by either producing a new substance at the electrode or dissolving the substance from the electrode. With a grasp of these principles, we can explore the different types of coulometry. Like a coin with two sides, coulometry also presents us with two major types. Now let's dive into these two fascinating types of coulometry: potentiostatic and amperostatic. Starting with the potentiostatic coulometry. This technique is also known as coulometry at controlled potential. Here, the potential difference between the working and reference electrode is kept constant, and the current is allowed to change. This potential difference is maintained using a device called a potentiostat. The beauty of potentiostatic coulometry is that it allows us to control the types of reactions that happen at the electrode by adjusting the potential. It's like being the conductor of an electrochemical orchestra, directing the performance by controlling the electrochemical potential. On the flip side of the coin, we have amperostatic coulometry, or constant current coulometry. In this case, the current between the working and reference electrode is kept constant, while the potential is allowed to fluctuate. This is achieved using an amperostat. The fascinating thing about amperostatic coulometry is that it allows us to control the rate of the reaction by adjusting the current. It's like setting the tempo for our electrochemical symphony, ensuring that the performance proceeds at a steady pace. So, you see, these two types of coulometry are like two different strategies to conduct the same electrochemical performance. In potentiostatic coulometry, you control the types of reactions by adjusting the potential, while in amperostatic coulometry, you control the rate of reactions by adjusting the current. It's just like a conductor choosing whether to control the types of instruments played or the tempo of the music. Now, you might be wondering which type of coulometry is better. Well, the answer is, it depends on what you need. If you need to control the types of reactions, potentiostatic coulometry is your way to go. If you need to control the rate of reactions, amperostatic coulometry is your best bet. Understanding these types leads us to the general characteristics of coulometric techniques, but that's a topic for our next scene. Stay tuned. So, what makes coulometric techniques stand out in the realm of analytical chemistry? Well, let's dive right in. One of the striking features of coulometric techniques is their high accuracy. This accuracy stems from the very principle of coulometry, which is based on Faraday's laws of electrolysis. These laws link the amount of substance produced or consumed at an electrode to the total charge passed through the cell. As such, the technique offers an inherent accuracy that's hard to beat. Along with accuracy, precision is another characteristic that sets coulometric techniques apart. In chemistry, precision refers to the closeness of two or more measurements to each other. Due to the controlled conditions under which coulometric analysis is performed, the results are often highly precise, providing consistent and reliable data. Another compelling feature of coulometric techniques is their ability to measure very small quantities of a substance. This makes them a valuable tool in trace analysis, where detecting and measuring minute amounts of a substance is essential. But, like all techniques, coulometry isn't without its limitations. For instance, it requires that the substance being analyzed is electroactive and that its reaction at the electrode is known. Additionally, it necessitates a complete reaction, which can be a challenge for some substances. Furthermore, the technique may not be suitable for substances that undergo side reactions, as this can interfere with the accuracy of the results. Coulometric techniques also require a stable known current or potential to be maintained during the analysis. This necessitates specialized equipment and can introduce additional sources of error if not correctly managed. Despite these limitations, the strengths of coulometric techniques far outweigh their weaknesses, making them an indispensable tool in analytical chemistry. With these characteristics in mind, we can appreciate the real-world applications of coulometry. From environmental monitoring to quality control in manufacturing processes, and even in medical diagnostics, the impact of coulometry is felt in many aspects of our daily lives. So, stay tuned to find out more about these applications in the upcoming scene. From laboratories to industries, coulometry has a wide range of applications. We've already delved into the theory, principles, and types of coulometry, and now it's time to see how this potent analytical technique is put to use in the real world. Let's start with pharmaceutical analysis. Coulometry is a popular choice for drug analysis due to its outstanding accuracy and precision. It's used to determine the active ingredients in a drug, ensuring that each dose is safe and effective. By measuring the amount of electrical charge needed to produce a reaction, scientists can accurately determine the purity of the drug compound. This helps maintain the highest standards of quality and safety in the pharmaceutical industry. Next, we have environmental monitoring. In a world increasingly conscious of our environmental footprint, coulometry plays a crucial role in monitoring pollutants. It's often used to measure trace amounts of harmful substances in water, air, and soil. For example, it can detect heavy metals in water sources, helping to safeguard our environment and public health. Coulometry also shines in industrial quality control. In industries like electroplating and battery manufacturing, maintaining consistency and quality is paramount. Coulometry helps achieve this by enabling precise measurements of metal coating thickness or battery capacity. For instance, in the battery industry, coulometry can measure the exact amount of charge a battery can hold, ensuring that each battery meets the required performance standards. But that's not all. Coulometry's versatility extends to fields like food and beverage testing, forensic science, and even art conservation. In each of these areas, coulometry's precise, sensitive, and reliable measurements are invaluable. In conclusion, the applications of coulometry are as diverse as they are essential. Whether it's ensuring the efficacy of a life-saving drug, monitoring the health of our environment, or guaranteeing the quality of products we use every day, coulometry plays a pivotal role. Coulometry, with its myriad applications, truly is a cornerstone of modern analytical chemistry. Today, we've journeyed through the intriguing world of coulometry. We delved into its theory and principles, exploring how this electrochemical technique measures the amount of a substance through the electricity consumed in its reaction. We've differentiated between the types of coulometry, potentiostatic and amperostatic, each with its unique approach and applications. We've also highlighted the general characteristics of coulometric techniques, such as their high accuracy, sensitivity, and ability to analyze small sample sizes. Furthermore, we've showcased the broad applications of coulometry, from pharmaceuticals to environmental analysis and quality control. In essence, coulometry is a powerful tool in the field of analytical chemistry, a tool that holds the potential to unlock new frontiers and propel us towards a deeper understanding of the world around us. Thank you for joining us on this fascinating exploration of coulometry. Remember, understanding is the first step to mastery. Subscribe for more because you won't find me later.